All right, so some of you guys asked for this video about doing different topics in calculus. So here's the first one. Excuse me. This is derivatives, okay? And so what happens in calculus, there's two types of problems. There's two main types of problems. There's a slope problem, and then there's an area problem. And both of those problems are used here in physics, okay? The first one is derivatives, all right? So when we talk about a derivative, right, so the derivative of a function at some point characterizes the rate of change of the function at this point. Okay, and the way you really think about this, you've been doing rates of change for a good portion of your math career, and the rate of change of the function is basically just the slope at that point. So we're going to apply that concept that you guys have learned of slopes now in calculus. Okay, now here's the basic process of what a derivative does. So you start with 2 points that are spread apart from the point you're trying to find the derivative at. So let's say I'm trying to find the derivative of the function at x equals 2. So the way that the derivative works is I start with points that are spread apart, okay? And basically what I do is I can find the slope of this line, okay? Now, because this intersects the graph at 2 points, this is what we call a secant line. But our goal is to get down to what we refer to as a tangent line, right? Where a tangent line is only going to intersect that 1 point. So now this gives me an estimate, right? And now I just kind of take 2 more points. And what you'll notice is that the difference between the 2 points, right, is now smaller. And now I'm starting to get a more accurate slope, right? So these 2 points now are decreased. And I keep doing that until, right, so if I take these 2 points, notice I'm almost right on top of my where I'm trying to find it now. Now once the difference between them becomes 0, now I have my tangent line. Now I can find the slope of this orange line that I just drew in there. That now becomes a derivative at that point. In math, right, what we say is the limit as the delta x approaches 0 of our function, and there's this whole big, it's f of x plus h minus f of x over h, or sometimes we'll say like delta x or delta h. In fact, we'll have to use the delta x notation because that's what we use in our limit. Okay, so plus delta x over delta x. Okay, so there's this big drawn out process where if I have the function, I plug in like f of x plus delta x, I plug in the f, x, and then I go through and I simplify it, and it just gives me a generalized version of the slope at any point. Okay, but what we're really doing is find the slope of this tangent line now. So finally, as your delta x between the points becomes 0, so as it approaches 0, we're making a line, thus making the line now a tangent line. Right? And remember, tangent line is 1 point, secant line is 2 points. So 2 points of intersection, 1 point of intersection. So now what we've done is now we found the derivative of the function at that point, right? Because derivative is signified, or mathematically is what we know as a slope, right? It's the rate of change at that point. Okay. Now, because the derivative is a slope, the notation will look very similar to what it looks like. So if I'm finding, let's say I want to find the derivative of a function, it'll look like this. So the ddx of f of x, right? So that would be my derivative. This is my derivative notation right here, okay, ddx. In physics, because most of the time our x function is t, it will look something like this, right? So if I'm looking for the derivative of a position function, which is actually the velocity, right? So it's ddt of x of t. And sometimes you can just write it as like dx dt, right? Like here, you can write this because f of x is also y. You can just say dy dx, right? So I'm finding the derivative of my y function. Some other ways that you can write the derivative is you can use a prime notation. So if I want to say, you know, velocity of time, I can just say it's the derivative of position. And this little notation, if you remember, like back in geometry when you did transformations, right? This is that prime notation. It's like a little apostrophe. Okay. Now, the good thing about derivatives in physics is there's only like really a handful of rules that you basically have to know. Okay. So you got the constant rule, the derivative of a line, the power rule, and then you can combine it all into one shot. It's called the sum and difference rule. Okay. So if I'm taking the derivative of a constant, so ddx or ddt of a constant number, right? That's just simply zero. Okay. What happens is derivative takes away exponents. Okay, and you'll see here when we do the power rule what I mean by that. But this is just the basic one. So if I have I define the derivative of a function and there's a constant in it, well, that part of the function is just going to be zero. Okay, the derivative of a line. So let's say y equals x. The one thing that makes it so if I want to find dy dx, okay, the derivative of a line is just, in this case, if it's y equals x, is 1, right? And you'll see here in a second what we mean by y becomes 1, but just remember the derivative of any line is a value, is a constant value, okay? So the way it works out is constants go to 0, lines go to 1, or whatever constant's in front of it, parabolas go to lines. So you kind of bump down in the exponent. And this next rule, the power rule, is how we figure that out, okay? So if we have y to the x, so we have our function is y equals x to the n, right? And I want to find the derivative of y. So I want to do dy dx. Okay. Now, I forgot to say this earlier, but how this is read is the derivative of y with respect to x. Okay. So my variable that I'm taking the derivative of is the x variable. Okay. The top part here, the y portion, that's my function. All right. So if I'm looking specifically at physics and I'm finding the acceleration, this becomes a v because acceleration is the rate of change of velocity. Right. So this becomes a v and this becomes a t because my x variable would be time. Okay. So the general power rule is very simple. What you're going to do is you're going to bring the exponent down in front. Okay, so I'm bringing the exponent down in front. Right, and I keep my function or keep my my variable, and then I'm going to subtract 1 from the exponent. Okay, so this is what I mean by a constant becomes 0, a line becomes 1 or a constant, a parabola becomes a line because you're chopping it off. Okay, so if you think about a constant, if I write that as as a function with x, right, and I follow my power rule, well, I bring 0 down in front of it, and then I subtract 1. So basically what happens is I have 0 times c times x to the negative 1. In fact, nope, that's okay, right? But because of this, 0 times anything is 0, right? Same thing here, right? X, my function is x to the first, right? If I'm doing the y equals x. So I bring down my exponent, and then I subtract 1 from it. So I have 1 times x, 1 minus 1 is 0. Remember, anything to the 0 power is 1. So that just leaves me whatever my exponent is, okay? Or if I have, there's an example here in a second. Okay, and the sum and difference rule is really just a way to, kind of break it apart, right? So you could do it all in one shot, but what the sum and difference rule says, if I'm taking the derivative of a function, and it looks like x plus or minus z, right? where they all have x functions, right? Or they all have pieces of x in it. All I can do is say, okay, it's going to be the derivative with the, oh, sorry, this should be a y. Right. So I'm given a function that's composed of y and z. And I want to find the derivative with respect to x, right? Well, that's just telling me that my answer is going to be the derivative of y plus or minus the derivative of z. Okay, so dy dx plus or minus dz dx. Okay, as you get further more into it, it just becomes easier to see, right? You don't really have to do this sum and difference rule. I'm just going to point it out because maybe it's easier for you to see it broken apart. Okay, so here are some just general math examples, right? So we're going to find the derivative of the following. So for part A, we got f of x equal to x cubed, equal to x cubed. So we're going to find the derivative. So we're going to do f prime of x, right? Because that's our derivative notation. That's what we're finding. So remember the power rule. So I'm going to take and put the 3 in front, and then I'm going to subtract 1, right? So constant, or excuse me, the exponent goes down in front, and then I'm going to subtract 1 from 3, so it's 3 minus 1, so it's squared, right? So the derivative of x cubed is 3x squared. Okay, so here's another example. Now, we didn't much talk about what happens if there's something in front, right, attached to my function. So we just follow our rule. Bring the exponent down in front and subtract 1 from it. So f prime of x, if I'm going to write the whole thing out, it's going to be 3. That's my exponent. The 5 is from my original function. And so then it becomes 3 times 5 times x squared, because 3 minus 1 is 2. So now I just multiply out 3 times 5. And so the derivative of 5x cubed is 15x squared. Okay, so now here's one that's a little bit more advanced, right? So we got, basically the same. We got part B plus something else, okay? So again, follow our rule, right? 5, bring down our 3, subtract 1. We have a constant, and we know the derivative of a constant is just simply 0. So we have 3 times 5 times x squared plus 0, right? And now we can just simplify this. So it ends up being 15x squared. So you can see that actually B and C, although the functions are different, right? So this is 5x cubed and this is 5x cubed plus 2. Notice that you get the same derivative, okay? It's because of the constant. Now here's one that's just a little bit more advanced, right? But again, just keep following the rule. Bring the exponent down, subtract 1. Bring the exponent down, subtract 1. Right? Bring the exponent down, subtract 1. Constant, 0. Right? And so if I collect it all, I got f prime of x equals, so 3 times 5 is 15. 3 minus 1 is 2. Now 2 times 10 is 20. 2 minus 1 is x, right? Is 1. Now I bring down the 1, right? Here's a line. We know it's 1 minus 1, so it's x is 0. It's just 1. So what is our answer? F prime of x equals 15x squared minus 20x minus 2, right? And then if I'm looking for a specific point, now I just plug that value in. So if I want to find like what is f prime of 2, right? Let's just say for part A. Now I'm plugging in 2, right? So I'm going to f prime of 2 is 3 times 2 squared, which is going to be 12, right? So that's telling me at x equals 2, the slope of the function, right, is 12. All right. So now let's see how this applies to physics, right? So physics has derivatives in multiple places. One of the first ways, in fact, when you look at a calculus book, is that they stack the free fall laps. Now, when I say stack, it's like you put them on top of each other. Okay, I'm going to run them side by side, but so this is my position versus time graph. Let's say I have a parabola, right? The slope, and if you just remember what does it mean, right? What is the meaning of a slope of a position versus time graph? Well, it's velocity. right? So at every point along the way, I'm going to do dx dt, right? Which means I'm finding the velocity. Okay? And so remember, parabola goes to line. So the velocity is the derivative of the position function, right? Well, if I do the same thing here for velocity, if I take, and you remember this, the meaning of the slope, so if I do dv dt, sorry about that, well, I'm finding the acceleration, right? And then a line goes to, a slope line goes to a constant line, right? So this is, let's just say, we'll just do general x squared. This would be 2x, and this would be x, or sorry, 2. So that would, these would be my functions. So y equals x squared, y equals 2x, or in this case, it'd be, let me write it in terms, I'm talking about in terms of physics, so let me write it in physics terms, right? Oh, I just erased my, okay? And so if I'm writing this function, this would be like position equals time squared, right? This would be velocity equals 2 times t, because velocity is the derivative of position. And then this would just be acceleration equals 2, right? Because if I take the derivative of 2t, it just becomes a equals 2. And if you look at the equations, right, for the functions, and we'll just write it as kind of the big version. So we know that velocity is the derivative of position, right? So if I go through and I take the derivative of the position function, look what happens. This is a constant, so that's 0. I'm not going to write it. This is to the first. That just becomes the constant. And now if I follow my rule, bring this down in front, right? And then chop off an exponent, so subtract 1. Well, 2 times a half is 1, right? And then 2 minus 1 is 1. So that just gives me the constant of acceleration. And then I've got the time function. So there's my velocity function. Okay? Now, we talk about how these functions or these equations talk about the constant value, or excuse me, constant acceleration. Here's why. So we know that velocity, or excuse me, acceleration is the derivative of velocity. So if I take the derivative of the velocity function, look what happens. Constant number becomes 0. This is to the first, it just becomes whatever's out in front. Right? And so there they are. And again, this is what you see in this kind of this stack, right, of the graphs. Okay? So now here's how that would work in, so for a problem. In fact, when you do these in math class, in calculus class, they often use a lot of the word problems are just simply physics problems. Okay? So if you got a missile fire from ground level rises x meters vertically upwards in t seconds as given by the function x of t equals 100t minus 12.5 t squared. Okay, and we're going to find the initial velocity of the missile, the time when the height of the missile is a maximum, and then the maximum height reached, and then the velocity with which the missile strikes the ground. Okay, so we're going to treat this as a math problem. So we're going to treat this using calculus. So for part A, remember the velocity function is the derivative of the position function. So if we take the derivative of 100t minus 12.5t squared, we get 100 minus 25t. Okay, again, and I'll show you that the power rule, right? We bring this down in front and we subtract 1. So 2 times 12.5 is 25. 2 minus 1 is 1, so that becomes to the first. Okay? Now, what is the initial velocity? Well, that's when t equals 0. Right? So all we're going to do is plug in t, or 0 for t. So we're going to say v of 0, which we now know what the function is 100 minus 25 times 0. Right? So that tells us that the initial velocity is 100 meters per second. Okay? Now, for part B, says the time and the height of the missile is a maximum. Okay, the maximum occurs when the final velocity, right, equals 0. So what we're going to do is we're going to set our velocity function equal to 0. We do 100 minus 25t. All right, so 0 equals 100 minus 25t. And so all we have to do is solve this. So plus 25t plus 25t. So you get 25t equals 100. Divide both sides by 25. You get t equal to 4 seconds. Okay, so we have initial velocity of 100. We have a time of max to maximum height of 4 seconds. Right? Okay, so now we're going to finish part C, which is now what is the maximum height? So it takes 4 seconds to get up to that maximum height. So we're going to find v of 4, or sorry, not v of 4, x of 4. All right, so we write our position function. So 100t minus 12.5 t squared. Okay, and so now we do is plug in the 4. So 100 times 4 minus 12.5 times 4 squared. I don't know why I did that. Okay, so 4 squared. Get my calculator. So we're going to do 100 times 4 is 400 minus 12.5 times 16. And so we get an answer of 200 meters. Okay, so it's going to go off the ground or launch up to 200 meters, right, being fired off at 100 meters per second. Okay, now part D is we're going to find what is the velocity as it strikes the ground. Well, in physics, as long as the acceleration is constant, there's a saying, the time to rise equals the time to fall. So it takes 4 seconds to get up to the maximum height. It's going to take 8 seconds to come back down to its original position. So now we're just going to do v of 8. And so that'll be 100 minus 25 times 8. Okay. And because our velocity function was 100 minus 25t. All right, so 100 minus 25 times 8. You find that it is negative 100 meters per second. Again, reiterates symmetry, right? If it leaves at 100 meters per second going up, it's going to come back down at 100 meters per second, but in the opposite direction. Okay, so that wraps up talking about derivatives in physics. The next video will be on integrals in physics, which is the other type of question in physics or in calculus.